EX66. So let's start with a small exercise and then we prove some properties of tensor product. So let's start with a very small exercise. So compute. This is principal idea, in particular Z module, the tensor over Z with the quotient of Z by Z. So still as Z module just. Okay. So the intuition might be this is 0 because I can move from left hand side coefficient into the right hand side, and so it's cute. But actually it's not, simply because 1 is not here, right? You can now write a tensor x like a1 tensor x and then 1 tensor ax and then 0. No, because 1 is not here. Okay, actually what we do is that we claim this is isomorphic to the quotient thing. So we construct a map, construct a Z bilinear map. So an element here could be written as an integer and times a. An element here is some x bar. I'm going to map it to, as you could see that you can never move this small a here. What you can only move is the n. So I'm just going to rewrite any element here into the form a tensor with an x bar. So let's check. This is Z bilinear. So this is obvious bilinear on the right hand side, the component x bar on the component NA. This both Z linear. Okay, and so this induces a map. So let me just write. This induces such a map. So actually, let's say any element here could be written. This is just, you could move Ni, just left A here and move all those Ni. Right? So basically, you could always write element of this format. So this is mapped. If you want an like sidebar. And let's say this is obviously surjective and injective. Okay, obviously this is surjective. Why it's injective? Because you can always write the element into this form. This is also, if the image x bar is 0, then this is an a tensor 0, and so this is injective. Kind of amazing thing. Okay, so second part of the exercise, let's prove some property. Let's first prove that for ideas I and j in R, there is unique R module. Isomorphism. Is R module. Okay, so obviously start with universal property, construct a bilinear map. X bar y bar is mapped to obviously x y bar, and checks this is bilinear, and so there is a unique map which maps x bar tensor y bar to x times y bar, and then we check this is isomorphism. How do you do that? You might directly check its surjective and injective, and you could also try to construct the inverse map. So let's first try to construct the inverse map. So let's start with R. Map to tensor product of R quotient I and R quotient G. Obviously this is R linear, and then notice that IR is in the kernel, because any element of the form is small I, this is mapped tensor 1, and so this is more rigorously, yes, this is it, and so this is 0. For similar reason, J is here, and so this induces our linear map. And maybe let's just check these two maps inverse to each other. So let's call this F and call this G. So F compose J maps element R to F of G of R is defined to be R1 tensor 1. And so F is defined to be just multiplication of the two. I take the bar, so this would be R and the take bar. Conversely, G compose F. Acting on whatever x bar tensor y bar. So this is G x y bar, and so x y 1 tensor 1, and so this is also equal to x bar tensor y bar. So then inverse to each other. So we avoid some computations. We avoid some direct proof of surjectivity and injectivity, but instead we just construct the inverse map of it. So let's say exercise 3. So before do that, let's put remark. Remark 1. For I equals 0, j equals 0, what we have proved is actually there is our linear isomorphism. Secondly, for r equals z, actually what we have proved is the same result as exercise 65. And this is just what is a plus b, this is dz, where d is greatest common divisor. This is exercise 65, we have already proved. Okay. So let's add a third remark also. Yeah. Third remark. So recall we have similar notation. So this map, our linear map, it has kernel I intersection with G, right? While this our linear map we just constructed had this kernel we have just proved I plus G. Okay, let's do the last part of our exercise. Still proposition for an ideal I R and R module M. There exists a unique R module isomorphism R quotient I times R with R is M, isomorphic to R module M quotient by submodule IM. And the map is R bar tensor M is mapped Rm bar. Remark. Particular take I equals 0. This implies that R tensor R with M is isomorphic to M. The map is of a generating element is generating tensor is this. Okay, so let's prove it. Again, let's start with bilinear map. So you have R, the coefficient R module, in the R module R quotient by I, the element small m, we map it to as claimed Rm bar. So this is well defined, which means for different representative of R bar, so they give you the same image. And so again, by the universal property, we got a map which maps our tensor M to, let's write it, our tensor M, it's our M bar. Good. Now let's prove its isomorphism. Again, let's construct the inverse map. So start with element M, map it to let's say one tensor M, right? And then show that this is in the kernel. Right? Because the element I am out of the form element from the ideal I times the element from M. This is mapped to one tensor I am by our linearity. So this is I tensor M, it's 0. And so it factors through this. So we got this map, let's call this G. Call this F. We want to show that G and F are inverse to each other, right? So G of F that take an element from this tensor product, let's say R bar, tensor with M. And so by definition, this is G of Rm bar. Rm bar, G of Rm bar is one tensor Rm. Right. For whatever lifting or whatever representative. And then this is R one tensor M. And then our bar tensor M. F compose G acting on whatever element small m bar. So this is F of one tensor M for any lift M of F M bar. So this is by definition again M bar. And so maybe a small remark is that any element, let's say Ri bar tensor Mi, could be written in that form because this is R is a ring, and so it has identity element. You can move outside this. So this is an element could be written in the form. Any element is an elementary tensor, in other words. And so it's enough to check that. Okay, so again, we are done. Remark. Following the remark before, second remark. We have the example, whatever Z module A, this is just third remark is that you have a map like this. You can check it. This is not isomorphism in general. Surjective, obviously. Let's check this is a bilinear map firstly. So this is idea of R, this is R module. And right, this is it. So let's say obviously this is R bilinear, and so it induces this map, which is surjective, but it's not in general injective. Counterexample is the starting exercise this video, which is Z tensor, quotient AZ, and we have proved this is isomorphic to this, but while this AZ has that Z module, AZ has the ideal of Z, let's say, with the Z module structure multiply with this Z module, this is 0. Okay, this is counterexample.